We will continue with the lecture 16 of this course. In the last lecture, we looked at how to analyze closed loop control systems, and then I explained that just like how we did with open loop systems, first we talked about how to analyze open loop systems in terms of inverting Laplace transforms and getting back the variables in time domain. And then we followed that up with notions of stability and how do you look at stability of these systems and so on. After that, I showed you that when you look at closed loop systems, essentially once you get the transfer function, then the analysis ideas and techniques are just the same as open loop systems. There is nothing that you need to know more to do the analysis. So, the stability ideas also largely translate to closed loop systems. So, remember in open loop systems we said if all the poles of the transfer function in the left half plane, then we said the system is stable. Similarly, as long as it is a transfer function, and I have already mentioned this, it does not matter whether it is open loop or closed loop, the ideas of stability will be the same. However, we are going to introduce another notion of stability through what we call as root stability table, and this becomes important when we talk about closed loop systems. This was not as important before in open loop, but in closed loop systems it becomes important. And I will speak to this in more detail later, but just to give you an idea, when we have these closed loop systems, let us say we have decided that we are going to implement, let us say, a P controller, a PI controller or a PID controller and so on. So, that just chooses the structure of the controller. Okay. So, if it is a P controller, then the structure says you have something called a gain, which is Kc. If it is a PI controller, it says the structure has something called Kc and tau I, gain and integral time constants and time constant, and if it is a PID controller, it is Kc tau I tau d. Now, we have not yet said how you are going to pick numbers for these constants or parameters of the controller. So, that is actually what is called as tuning, and before we understand tuning, I am going to explain some notions of stability so that I can then tie it in with how tuning is done. So, the difference that is going to come between open loop transfer functions and closed loop transfer functions is that in open loop transfer function you have already identified a model. So, you know all the parameters of the model and all of these are numbers in a transfer function. However, when you notice the closed loop transfer functions that we saw in the last lecture, you see that in the transfer function there are these parameters of the controller such as Kc tau I tau d, which are yet to take values. We have not given them values. So, in that sense, what happens is the denominator polynomial and of course the numerator polynomial also, the coefficients that multiply the powers of s power 0, s power 1, s squared, s cube, s power 4 and so on, they become a function of these controller parameters. So, they are not just numbers, but they now become functions of these controller parameters. So, in that sense then the roots of these polynomials are not known, or the roots take certain values depending on what values you give for this controller coefficient. So, we will get to a stage where we have to analyze the denominator polynomial to understand stability. However, the denominator polynomial have coefficients, polynomial coefficients which are actually functions of controller parameters. So, that will bring in some complexity in the analysis that would require us to introduce the next notion of stability. If that were not there, if we were actually going to say, look, I am going to put these numbers for these controller parameters and then I want to check stability, then for each set of controller parameters you can use the same ideas, you do not need anything new. But when we actually let them be functions of the controller parameters, then you need some new ideas, and that is what I am going to cover in this lecture today. So, remember the open loop transfer function g of s, we will have a numerator by a denominator form. The controller can also be thought of as a numerator by a denominator form. For example, if the controller is simply Kc, then the numerator is Kc, denominator is 1. If it is a PID controller and then you have Kc 1 plus tau is, then this can be simplified as Kc times tau is plus 1 by tau is. So, this is the numerator polynomial, this is the denominator polynomial. So, in essence whatever we are doing, we can always write this in the numerator by denominator polynomial form, and then once we have this, we know the closed loop transfer function which we have seen several times. The closed loop transfer function is basically GPC by 1 plus GPC. So, if I write Gp as Ns over ds and C as C1 over C2 and I do the simplification, then I will get something of this form, which is again some numerator by denominator form, right. So, the closed loop transfer function also is some numerator by denominator form. So, when we talk about stability, we are going to say y is some closed loop transfer function times y set point. Okay, so, what we want to know is whenever this is stable, that is we do not ask for set point changes which are unreasonable, crazy, then when will this still be stable is a question that we are interested in answering, and we know the answer to this question. This will be stable if the poles of this transfer function are strictly in the left half plane, right. Remember, so I have this just as reminder. So, I have an imaginary axis, this is the right half plane which includes all of this area, this is the left half plane. Now, as long as every pole is strictly in the left half plane, then I will have a system which is stable. Even if one pole goes either to the right half plane or on the imaginary axis, then the system can become unstable even for reasonable y set points. It is very clear why if there is a pole here, then the system will become unstable. We also discussed this, and I just want to recall this here, is if I have, let us say, a pole on the imaginary axis, then if I give a sine oscillation at exactly this frequency, then I talked about resonance and how things will become unstable. So, if there are poles on the imaginary axis, still you have to worry about it, they are not strictly going to be stable for all reasonable set point y's, right. So, for that to happen, the poles of the transfer function should be strictly in left half plane. That basically means it does not matter whether you are looking at open loop transfer function or a closed loop transfer function, because we are always going to write these transfer functions as a numerator by denominator form. Then basically what you are going to do is you are going to look at the roots of the denominator, and as long as the roots of the denominator are strictly in the left half plane, we call the poles as being in the left half plane, then we say the system is stable. Now, if you actually knew the value of this and this, then once you substitute this here, all you are going to get is you are going to get a transfer function form where there is a numerator and denominator. What you can simply do is take the denominator polynomial and maybe send it through, let us say, a MATLAB code to find the roots of that polynomial, and that is what I call as writing the polynomial in a root resolve form. So, for example, if I have a polynomial which is third order, if I simply write this as whatever the values a3 s cube plus a2 s squared plus a1s plus a0. So, this is third order polynomial. If you specifically write this in some form where you have something like a3 times s minus root 1 times s minus root 2 times s minus root 3, right. If you write like this, then this is what I call as a root resolve form, and we know the advantage of this, because when we do the partial fraction in this root resolve form, we know that the terms that are going to come are of the form e power r1t, e power r2t, e power r3t and so on, and if these roots repeat, then you know the corresponding form from what we have seen before. Okay. So, as long as you get this in a numerator by denominator form, the closed loop transfer function, and then if you have the values k, c and tau I, you can really figure out whether the closed loop is stable or not. It is a very simple computation to do. However, now if I ask you a slightly different question, I ask you this question, I am not going to give you the values of k, c, tau I and tau d, okay, because those are things that I need to find. I do not have values for this, and instead of doing this here, what we are saying is give me k, c, tau I, tau d, then I will tell you whether the system is stable or not by simply doing this root finding. But if I flip the question and then I ask saying, okay, I have k, c, tau I and tau d as parameters themselves, you tell me for what values of k, c, tau I and tau d the system will be stable. So, there is a subtle difference here, right. So, what I am asking you to do now is I am telling you I am not going to give you values for k, c, tau I, tau d, but I want you to tell me what are reasonable values for k, c, tau I, tau d, or what are values for k, c, tau I, tau d that will still keep the system stable. Okay. So, that is a very different question than what is the stability of closed loop. Okay. So, when we want to do this, then it becomes problem. The problem is the following: you might simply ask, think about this and say, well, there is a polynomial in the denominator, and basically I can write the roots of the polynomial in some form and then look at the roots and answer that question for this kc tau I and tau d. So, for example, all of us know this formula that we have been told several times and it is drilled into our memory is the root of this quadratic equation, which is minus b plus or minus root of b squared minus 4ac by 2a. So, you might say let me write this polynomial, get the kc tau I tau d as b, ac as functions of those, and then I will look at this, and then from this I will be able to find out whether the root is going to be in the left half plane or not, and what values of kc tau I and tau d will retain the roots to be in the left half plane. So, this is possible if the denominator polynomial is, let us say, a quadratic, and when it becomes a cubic, this is a much more complicated formula, and beyond that there are other mathematical problems in terms of writing analytical expressions for the roots. So, I am not going to get into the theory of that and then the complications that surround that, but as far as this course is concerned, you can assume that beyond a certain order it is not possible to write these analytical forms for us to do this exercise. So, that brings a very interesting question where I have a polynomial and I have the coefficients being functions of kc tau I tau d, and if the order is large enough I cannot get analytical expressions for the roots. But I want to answer this question where I ask what values of these constants will still keep the poles in the left half plane. So, conceptually it is an interesting thing to think about, right. So, what we are saying is, can I guarantee that the poles will be strictly in the left half plane without actually calculating the poles? So, that is a very interesting question, which is very different from the partial fraction idea that we had till now. So, in the course introduction I mentioned that I will introduce different ideas whenever they are very required and not just as another idea that people talk about, and here is a point where partial fractions are not useful anymore. I cannot really do this with partial fractions because for partial fractions I assume that I know the roots, but here I do not know the roots, and if the order is large enough I cannot compute the roots analytically. However, I still want to find out when the roots will be in the left half plane without actually computing the roots. So, it looks like it is a very interesting mathematical problem, and the nice thing is that there is a solution to this, which is called the root stability test. So, what I am going to do is I am going to explain this root stability test in terms of the procedure and the rules that you should follow to do this root stability. Why these rules are true and why root stability test works and so on are things that I am not going to explain here. So, you might just take this root stability as a very interesting procedure which is going to tell us if all the roots are strictly in the left half plane without ever computing the roots. Okay. There is complete mathematical proof for this which we do not have to worry about in this course. Just be assured that it is actually mathematically proved. So, this general problem I am going to pose is the following. So, let us say I have a polynomial of this form a naught s power n, a1 s power n minus 1 all the way up to a n equal to 0, and then clearly the roots of this polynomial are going to be, let us say, or we can plot the roots of this polynomial in a complex plane. So, this is the imaginary axis and this is the real axis. So, if the roots are real, they will be on the real line. The minute they are imaginary, they will be here, and if they are complex, they will be existing in these regions of this complex plane. So, what our interest is in basically guaranteeing for a polynomial. So, also let me set context. So, this polynomial, if you are looking at Gp of s is ns by ds, or it could be some closed loop transfer function which is ns by ds. So, we are always looking at the denominator polynomial. Okay. So, the denominator polynomial is what this is, and what we are trying to see is if we can guarantee the roots of this never fall back into the right half plane. Okay. If I can guarantee that, then I know this polynomial will lead to a stable open loop, stable closed loop and so on. So, that is what we are trying to do. But through some mathematical trick we are trying to do this without actually computing the root, and the reason why we do not actually compute the root is because some of the coefficients are functions of the control parameters. So, that is a logic that I want you to keep in mind, so that you see why we are doing all of this, not as just some root test that we learn. So, now let us go through a procedure, and then what I am going to do is I am going to take several examples and run through this procedure, so that you understand how these computations are done, and once that is done, then we will go on to the tuning of controllers and looking at the values for Kc, tau I and tau d based on the ideas that we have here. Okay. So, the very first step is you should check whether A naught is positive. Okay. Now, if A naught is not positive, then basically what you do is you multiply the whole equation by -1 and make A naught positive. Okay. So, the first thing is you can always make A naught positive is something you should know, and once you have a positive A naught, then if even one coefficient in the polynomial is negative, then you are guaranteed that there is at least one root in the RHP and the system is unstable. Okay. So, you automatically immediately know that the system is unstable. So, this is the first result. Okay. So, first make A naught positive and then look at all of these coefficients. You do not have to worry about A naught, which we have already made positive, then A1, A2, A3, A4 all the way up to An. Even if one of these coefficients become negative, then you are guaranteed that there is a pole in the right half plane and your system is unstable. So, that is a very interesting result. Okay. So, then you know already there is some problem here. Now, if you really want to figure out how many poles in the right half plane, then what you do is you do this procedure. So, you take the highest power and then put the coefficient corresponding to the highest power in the first row. So, you also write this so that you kind of keep track of what is happening, and then you leave the one which is corresponding to s minus 1 and then go to s n power n minus 2. So, basically you skip one term and then keep adding constants here till you run out of terms. Okay. Very simple procedure. Okay. And we will show this through many examples in this lecture, so that you are comfortable with this procedure. So, take the first one and then put the corresponding power here and then leave one term, go to the next term, leave the next term, go to the next term, leave the next term, go to the next term, and so on, and you keep filling it till you run out of terms. The second row you put s power n minus 1 here. Okay. So, if this is a fifth order polynomial, this will be s power 5, this will be s power 4. This is just to show you how many rows will come in. So, you are not going to really use this anywhere, you are going to only use these numbers here. Now, what you do is you start with the second term in the polynomial and then you skip what was already used in the previous one, use alternate. Okay. That way all the left out coefficients starting from here to here gets filled up in the second row. So, the first two rows are really directly filled out based on the polynomial under consideration. Okay. So, once you have that, every other row is computed based on these coefficients, and we are going to show you a rule to figure out how you can use this construction to identify if there are roots in the RHP and how many roots are in the RHP, right. So, to summarize again, the first two rows are filled out of just the polynomial that we are looking at currently, and for the first row you are going to just to show that this is the highest power s power n, you are going to take the first term and then put the coefficient and then skip one term, put the coefficient, skip one term, put the coefficient, and so on. And in the second row you are going to write s power n minus 1, and all the left out terms you are going to just put the coefficients here. Okay. Now, once you do this, then you can start filling one row after another. Any time you fill another row, you basically say s power n minus 2, s power n minus 3 in the reducing order here. So, if I want to get B1, so the rule is very simple. To get B1, what I do is I multiply this and subtract a multiple of this and this and divide by A1. So, which is what is here A1 A2 minus A0 A3 by A1. Okay. Now, if I want B2, then what I do is I multiply A1 A4 minus A0 A5 by A1. Okay. So, that is B2, so and so on. So, you repeat this procedure. So, if B3, then you multiply this by this divided by A1, and so on. Okay. Now, when you come to the next row, you basically follow the same procedure, no difference, except that for filling out any row you only look at the two rows above that row, that is all. Okay. So, once you have two rows, to fill the third row you use row 1 and 2, to fill the fourth row use rows 2 and 3, to fill the fifth row you use rows 3 and 4, and so on. So, recursively you will be able to fill this till there is nothing more to fill, and I will show you how that happens. So, if I use the same rule here for C1, I should do B1 A3 minus A1 B2 divided B1. That is what I have. If I want C2, I should use B1 A5 minus B3 A1 by b1 and so on. So, you can keep doing this, and since I am going up to s power 0. So, if I have an nth order polynomial, I will have n plus 1 rows here that are filled out. Okay, so, I hope this procedure is clear. We will look at examples down the line to understand this procedure in terms of the mechanics of these computations. Now comes the really fascinating part of this table, right. So, what then, right. So, what the root stability criterion says is that if I start with a positive number, okay, and if I have all of the first row as positive number, then there are no roots in the RHP. So, that is an interesting result. So, if there are no sign changes is what we say. When we say no sign changes, because I start with A naught which is positive. So, if everything else remains positive, there is no sign change from positive to negative. Okay. So, if there are no sign changes, then there are no roots in the RHP. Now, the number of roots in the RHP can be shown to be equal to the number of sign changes in this polynomial. So, for example, the first one is a positive number, let us say, the second one is a negative number, and everything else then remains negative. There is only one sign change. So, there is only one root in RHP. Okay. Now, let us say the first number is positive, second number is negative, the third number becomes positive and everything else stays positive, then there is one sign change here, positive to negative, another sign change from negative to positive. So, there are two roots in RHP and so on. So, as long as you do not get any zeros in the first column, the rule is very simple. The number of roots in RHP equal to the number of sign changes. So, notice something very interesting that mathematics is allowing us to do. What we are saying is we know how many roots are in the RHP, which is like an infinite region. However, I can actually never computed the roots. Okay. So, that is a very interesting idea that you want to remember. Now, if one of these goes to 0, then we are going to do some small trick. So, we are going to use think about this as a very small positive number, and then we are going to see whether the next one is positive and so on. That will tell us whether there are roots in RHP, and I will show this using an example. But when we get zeros, then we always have to worry about what happens then. So, zeros generally indicate that I have roots on the imaginary axis. Okay. So, whenever we have 0, we might still make judgments about how many roots are in RHP, but this indicates that there are already roots in the imaginary axis. So, that is something that we have to remember when let us say the first column has 0. And the reason why we worry about 0 in the first column is because, remember, in the calculation procedure I showed in the last slide, every time we divide by the first number in the row above. So, since we are dividing by the first number in the row above, if that number becomes a 0, I have a problem. So, that is the reason why 0 is a particular issue here. Okay. Now, there are cases where the whole row could be 0, in which case we need to fill that with something to complete the procedure, and I will explain that with examples. Okay. So, these you can consider as more cases that are usually not the rule. I would not really say exception, because there are many times where you have poles on imaginary axis, but these are considered separately. But if these were not there, the procedure is very simple. You simply say, I start with A naught, fill the table, and I find out how many sign changes are there, and the number of roots in RHP is equal to the number of sign changes that I have had. Now, it is very interesting to note here, again I would like to repeat this, because these are kind of things that makes some of these topics very interesting, that we are actually saying how many roots are there in RHP without actually computing the roots. Okay. So, I could say there are 2 roots, but if you ask me what those are, I do not know, right. So, that is an important thing that you want to remember. So, let us take some examples, then look at how this process is done. So, I think I have 3 or 4 examples in this lecture, so that we will go through those, which will kind of look at all the cases that we have discussed, and then we will show you how most of the cases that we have you can handle quite easily. So, let us take this first example, which is a 5th order polynomial. So, automatically you know that there must be 6 rows. Okay. So, row for s power 5, s power 4, s cube, s squared, s power 1 and s power 0. And as I said before, the first 2 rows are directly filled in with the numbers given in the polynomial. So, the coefficient of s power 5 is 1. So, I have 1, then I skip 1, then I have 24. I skip 1, I have 23. Now, the next row is s power 4 row. So, since I have already taken this, I start here, I skip 1, I take this, I skip 1, I take this, I have 8, 34, 6. Okay. Now, let me show you just these two numbers, and then you can actually, since this is on the screen, you can simply repeat the computations by hand yourself, so that you get comfortable with how this table is. Okay. So, how do I get this number? This number I get by 24 times 8 minus 34 times 1 divided by 8. So, if you do this computation, you will get 19.75. So, that is how I have got this number. So, how do we get this number here 22.25. So, 22.25 I get by 8 times 23 minus 6 times 1 divided by 8. So, I get this number. Okay. Now, when you come to this number clearly, so when I wanted to do this, I took this and this here, right. When I wanted to do this, I took this and this. So, when I want to do this here, I have to take this and this here, but these are not filled. So, they are 0. So, whatever multiplication you do, you will get a 0. So, that is how you get a 0 here. So, I think about this as just for the sake of understanding, say this is 0 0. So, this will be 8 times 0 minus 1 times 0 by 8, which will be 0. Okay. So, that is how you get a 0 here. Now that this is filled, then you can fill the next row. So, if you want to fill this right here, so that is going to be 24.98, you will have 19.75 times 34 minus 8 times 22.25 by 19.75. So, this is what this will be. Okay. Now, if you want to do this, this is easy to see. So, for example, then you have to use this and this column. So, 6, the way I compute this is 19.75 times 6 minus 0 times 8 by 19.75. So, this and this will get cancelled at 6. So, you can do this computation and fill each one of these elements right now. Okay. Now, you are done. Okay. Then you look at the first column and then look at how many sign changes are there, and you will notice that there are no sign changes. So, we can categorically say that there are no roots in the RHP. So, this system is stable if there is a transfer function which has this polynomial in its denominator. So, number of sign changes 0, number of RHP poles 0. Now, out of curiosity, if you were to go and do the poles for this, these will be the poles, and you see all of them are in the left half plane. So, let us take the next example that we have. So, here again I have 5th order polynomial s power 5 plus 4s power 4 plus 6x cube 6x squared 5s plus 2. Again the first I put here and the coefficient is 1, skip 1 6, skip 1 5, and then you do the second row s power 4, first coefficient is 4, skip 1 6, skip 1 2, you have this, and then basically just let me show you one computation again just for completeness. So, this 4.5 is going to be 4 times 6 minus 1 times 6 by 4. Okay. So, 4 times 6 is 24, 24 minus 6 is 18, 18 by 4, 18 by 4 is going to be 4.5. Okay. That is how you got this. Okay. So, you do this here. Now, when you come to this part here, now you do the same formula, which is 2 times 4.5 minus 2 times 4.5 by 2. So, that is 9 minus 9 by 2, 0. Okay. So, this will turn out to be 0. The problem with this 0 is that when I come here, if I leave it as a 0, then I will have 2 times 0 minus 2 times 0 by 0. So, 0 by 0 form will not make any sense mathematically as far as this computation is concerned. So, what we are going to do is we are going to assume that this is not 0. The fact that it has become 0 tells us something, but at least as far as just saying purely on the right half plane, we can make this as epsilon, which is a very small positive number, and then we compute this number here. So, to compute this number, what happens then is you have 2 times epsilon minus 2 times 0 divided by epsilon, the same procedure that we have been using. So, this will give me 2. Okay. So, now when I look at this first column here, I will notice that there are no sign changes because I am assuming this epsilon is a small positive number. So, there are no roots in the RHP. However, the fact that this has become 0 tells me that there will be roots on the imaginary axis, and it will turn out that there are roots on the imaginary axis, and all the other roots are in LHP. So, nothing in RHP. So, that is another example. Now, the next example I am going to show you is what is called the use of auxiliary polynomial. So, here let us take a 6th order polynomial, which is of the form s power 6 plus 14 s power 4 plus 49 s squared plus 36. So, I am going to do the same thing. So, s power 6 I am going to take the first term, skip the second term which anyway is not there, s power 5. So, I take 14 here, and then skip s cube which is not there anyway, and then I get the s squared term, and s power of 1 is not there and I get 36. So, basically if you think of this as s power 6 plus 0 times s power 5 plus 14 times s power 4 plus 0 times s cube plus 49 times s squared plus 0 times s plus 36, and then use the same procedure that I am going to take 1, skip 1, 14, skip 1, 49, skip 1, 36, that is what I have. But unfortunately I need 2 rows to be filled up. If I do not do anything, basically I will have 0, 0, 0, 0 here, right. So, these are the only things that I will have. So, the way this is taken care of in this root table, again this I am going to tell you like a rule, like a heuristic, but there is a sound mathematical reason why all of this is done, is that somehow I am going to fill this up, but already I know this row is all 0, right, and I have already said when you have rows 0, then you are guaranteed that there are poles or roots on the imaginary axis, right. But nonetheless, for us to finish this process I have to get something going here. So, the way we are going to do this is we are going to take this polynomial s power 6 plus 14 s power 4 plus 49 s squared plus 36. Okay, so we know if we differentiate once I will get the s power 5 s cube and s term. So, we differentiate once and then this will become 6 s power 5. So, this is just a procedure, I am not telling you why you should do this, but I am telling you by differentiating this you will get these terms which were 0, so that you can actually fill that out in the table. And the reason why it works is beyond the scope of this class, but this is a procedure that you can follow. Now, this is 14 times 4 is 56 s cube plus 98 s plus 0. Okay. So, if I were to put these terms here, then instead of 0 which was the s power 5 term, I put 6 here, and instead of 0 which was the s cube term, now I have 56 here, and 0 instead of this term I have 98, and the last term is 0 because I have run out of terms here. Once I have this, then basically I follow the same process whatever I have shown you, and then I look at the first column and I see that the first column has no sign changes. So, there are no roots in the RHP. Okay. However, because of this 0 I know that there are roots in the imaginary axis, and in fact it turns out the roots are 2i minus 2i, I minus I, 3i minus 3i. So, you see all the roots are in the imaginary axis, none of them on RHP, which is again guaranteed using the root stability table. So, let us look at one last example to understand this, and then we are basically done with this portion of understanding the stability of closed loop system. So, now I have a simple 5th order polynomial. We are going to do the same thing. The first one s power 5 1 2 21, and corresponding to s power 4 I have 2 12 and 10. 2, 12 and 10, then I do the same procedure. So, let us just do this one term here. So, this is going to be 2 times 2 minus 12 times 1 divided by 2. So, this is going to be 4 minus 12 by 2, this is going to be minus 8 by 2 equal to minus 4. So, that is the number here. So, if you do this computation the same way that we have done, the next number will become 20, 18, 10 and so on. Now, if you ask the question as to how many roots are in RHP, you would say that there are 2 roots in RHP, because there is one sign change here from positive to negative, and then another sign change here from negative to positive. Okay. So, if you look at this right now, this is a root in the LHP, this is also a root in the LHP. However, this is a root in the RHP, this is a root in the RHP, this is a root in the LHP. So, this has 2 roots in RHP and 3 roots in LHP, which we can actually find out by just looking at this, because there are no zeros here, there are 2 sign changes, that means there are 2 roots in RHP, and since it is a 5th order polynomial, the remaining 3 roots are in LHP. But look at how remarkable this is. We do not know what the roots are. This is actually I am showing you the roots or the poles after computing, but if you just stop here, okay, this is you did not know this, that these are the roots, you would still simply be able to say, look, there are 2 roots in RHP and 3 roots in LHP. I do not know what those are, but this is the true situation, and that is actually correct. So, that is quite an interesting idea when it comes to. So, basically I introduced this notion of root stability test or root table because I think this is an idea which goes beyond partial fractions, in the sense that for us to do partial fractions we have to be able to find the polynomial in a root resolved form and follow through, and once you have it in a root resolved form, then it is basically a question of simply looking at the roots and then seeing whether they are in LHP or RHP to figure out stability. However, I tried to explain to you the idea that when you have these closed loop systems and you have these controller parameters, you do not know the values of these controller parameters. So, we are going to make judgments about the stability of the closed loop system, keeping the controller parameters as they are without assigning them values. And that becomes complicated because higher order polynomials you cannot write analytical forms for the roots. So, we need to find some other way, and this root test is a remarkable idea which allows us to actually figure out how many poles are there or roots are there in LHP and RHP without actually computing the poles. So, that is what I showed in this lecture. In the next lecture I am going to show you how we are going to use this in tuning controllers and so on. So, I will start with what are the different ways in which we can think about tuning controllers and how all of this falls together. So, I will see you in the next lecture. Thank you.